So, we are going to talk about the blood flow to the heart and its relevance to Bernoulli's principle. So, we know that blood flows through the heart and the inner walls of the blood flows through the arteries, and the inner walls of the arteries have elasticity, or they are elastic in nature, and because of that there is a smooth flow of blood. However, if there is an increased blood pressure, these elasticity could be affected, and in which case it will lead to damage of the artery and the smooth blood flow will be interrupted. And this is related to the elastic properties of the arteries, which we have seen while we have discussed the elastic properties of matter. Now, we are specifically going to talk about blood flow to the heart and the pumping of the heart. So, what happens is that blood flows to the heart through coronary arteries, and because of various reasons which include age and as well as unhealthy lifestyle, or rather unhealthy food habits, plaques accumulate inside the arteries, inside the walls of the arteries, and otherwise there is a smooth flow of blood through the arteries and they reach the heart. So, these are oxygenated blood, and blood pumps that oxygenated blood and sends it to various parts of the body. However, if there is a plaque deposition in the inside of the artery, then what happens is that the flow of blood gets choked, and when it gets choked, the flow gets interrupted, and there is the smooth flow of blood to the heart, oxygenated blood to the heart gets affected. So, these are some of the symptoms that one sees in heart disease. So, how is it related to Bernoulli's principle? So, what happens is that so we have so these arteries. So, these are the arteries, and there are in the inner walls of the arteries there are plaques that form. So, these are the plaques, and this is basically the artery. Specifically, the arteries which carry blood to the heart are called coronary arteries. So, let us say this is one of the coronary arteries. So, because of this restricted flow of blood, the heart would still pump, but will not get the oxygenated blood as would have otherwise arrived in a healthy case. So, what happens because of that is that if one or more coronary arteries gets completely choked because of this plaque that you are seeing here, that will lead to heart attack. Let us see Bernoulli's principle, how is it related to understanding of heart attack. So, Bernoulli's principle, just to remind you, says that the kinetic head plus the potential head plus the pressure head is constant for an incompressible fluid, non-viscous incompressible fluid. So, as there is a blockage in one of the coronary arteries that is carrying blood to the heart, so the heart would pump, and when it pumps, the blood will rush through these arteries that will change or rather increase the kinetic head or the kinetic energy. At this moment, let us forget about this potential head and not take it into serious consideration here. So, if this kinetic head increases because of the increased rate of blood flow, then the pressure will fall. So, if the pressure falls, pressure inside the arteries fall, and when it falls, the external pressure that tries to collapse the artery, and when it tries to collapse the artery, the heart pumps stronger or faster, and if that happens, then of course there is again a rush of blood. So, the velocity increases, which ultimately increases the kinetic part of this principle, and again the pressure falls, and repeated occurring of this leads to heart attack. Okay. So, when the pressure falls inside the artery, because of the pressure from outside will try to collapse, the heart tries to resist that and pumps faster, and the speed of flow or the flow of blood increases through the artery, which will lead to further drop in the pressure. Okay. So, this is the example of Bernoulli's principle in human body in relation to the heart attack. So, let us talk about the next topic, which is called as the viscosity. Is basically a property of the fluid, just like that we have seen in surface tension. So, suppose we have an ideal fluid. Ideal fluid means the fluid which is a non-viscous fluid, it does not have viscosity. Consider the flow of such a fluid inside a pipe. So, this is a pipe, and we have a non-viscous fluid, an ideal fluid. So, an ideal fluid means non-viscous fluid. So, let us see in this fluid different layers of the fluid. So, all of these layers of fluid which is flowing through this pipe move with the same velocity. Okay. However, for non-ideal fluids, or rather the fluids that are really seen in everyday life, those all have some viscosity, and because of that, what happens to this same flow is the following. So, the drawing has not been very good, but what I am trying to show is that each of these layers actually move with different velocities, and the layer that is right at the middle of the pipe, that moves fastest, that is with the greatest speed, and the one that is in contact with the periphery or the inner wall of the tube, it does not move at all. So, the velocity gradually decreases. So, let us call this velocity as V1, this one as V2, this one as V3, this one as V4, and then let's this velocity v5 which is equal to 0. So, we have v1 greater than v2 greater than v3 greater than v4 and of course, greater than v5 which is equal to 0. So, that means that the inner the liquid which is right at the center moves with a much bigger velocity than the velocity that is there with the which is here which is just in contact with the inner wall of the tube, does not move at all. And this happens in viscous fluids. And one practical example, you can always see that even though a car is driving very fast, there will be a thin layer of dust which will stick to the body of the car and will never go away no matter how fast the car is moving. That is because of the fact that that thin layer of dust has 0 relative velocity with respect to the car, and it will always be there and will not get wiped off even if the car is speeding. So, let us have a quantitative understanding of viscosity, and for that let us take this figure . So, there is a viscous fluid enclosed here, which has in between two slabs of area A, the cross sectional area A for both the bottom for the top and the bottom here, and it encloses viscous fluid. So, now what happens is that we will apply a force to the top layer. Okay. And the figure becomes like this. So, this one this top layer which is here, it moves with a velocity v, and the the bottom layer has got a velocity is equal to 0, and let this height be h. So, over a height h, the fluid layers, now this is called as laminar flow, because each of these the disc or the layers that we have drawn, layers of the fluid that we have drawn, is called as a lamina and that is why this is called as a laminar flow. So, the top lamina is moving with a velocity v because of the application of this force, and the subsequent lamina below that are moving, but moving with lesser velocity, and the velocity actually goes down to 0 as you come down to the bottom layer. And more the viscosity of the fluid, more force would be required to keep it in motion. And so, as each layer moves, it is subjected to a viscous force from its neighbors. So, each of these layers face a viscous force from the layer that is immediately below or immediately above. And so, this applied force, the job of this applied force is to compensate for this viscous force. And this force that we have just discussed, this force, the applied force depends on A, the surface area which we have shown here, the surface area of this top surface or the bottom surface area A, and so this, it's a direct proportionality, F is proportional to A, it is the speed V, and F is proportional to V, and finally, it also depends upon this height h, and F is in fact inversely proportional to h. And if we take into all these dependencies of this applied force F, which as I said compensates for the viscous force that exists between the layers or the lamina of the fluid, then F is proportional to A V over H, and we can write it with as an equation by introducing a constant called as eta, where eta, this is called eta, eta is called as the coefficient of viscosity. So, this force that is needed to keep the top layer in motion and the subsequent layers will follow with gradually lesser and lesser velocity, with the ultimately the bottom layer will not be moving at all, just the way we have seen it, flow of the liquid through a pipe, and this motionless situation happens because there is a strong interaction between the fluid molecules or the liquid molecules along with the molecules of the this cover or this the container or the pipe or whatever it is through which the fluid is flowing. And we said that the more viscous the fluid is, the greater would be the force required. And so, basically we know the examples of viscous fluids as maybe glycerine or honey, they are quite viscous fluids, and this force would go as eta A V over H, where eta is called as the coefficient of viscosity, A is the area of cross section of these various layers, V is the speed of the top layer, and H is the height over which the fluid is confined. So, now to know about the coefficient of viscosity, let us see that this coefficient eta is equal to F H divided by A and V. So, F has unit as Newton, H has in meter, A is in meter square, and this is meter per second. So, this is equal to Newton per meter square into second, or this is also called as a Pascal second. So, the unit of this coefficient of viscosity is called as Pascal second. Pascal is 1 Newton per meter square. There is also a common unit, or rather the commonly used unit is called as poise, and it is written with a P. So, 1 poise or rather one poise is equal to 0.1 Pascal second. So, it is simply divided by a factor of 10 the Pascal second is divided by a factor of 10 in order to get a poise. So, that is the practical unit or commonly used unit for the coefficient of viscosity. So, let us see now some of the fluids. So, viscosity of some of the common fluids. So, fluid, and as we have done earlier, almost in all cases, that there is a strong temperature dependence or at least there is some temperature dependence even if it is not strong. So, we will have to mention the temperature at which the viscosity is calculated. So, fluid and temperature at which it is calculated and the value of eta or call it a viscosity. Now, this is expressed in 10 to the power minus 3 Pascal second. So, let us take air at 0 degree centigrade, it is equal to 0.0171, and as I have written that it is 0.0171 into 10 to the power minus 3 Pascal second. Then for helium, it is 20 degree centigrade, or we can say that the temperature actually measured in degree centigrade. So, it is at 20, it is equal to 0.0196. This is blood. When I say blood, I usually mean whole blood. There is also another component, or rather one term called as blood plasma, which varies from the whole blood by just a little bit. We just quote this value even while we have quoted for surface tension and others, we have quoted it for the whole blood. It is at 37 degree centigrade and the value is very close to 4. Glycerin, which is known to be a very viscous fluid, it is at 20 degree centigrade, this is 1500. So, 2 orders of magnitude more than this, and at least something like 6 orders of magnitude more than the gaseous 2 entries here. Then it is methanol at 0 degree centigrade, it is 0.584, and of course, we have to quote water, which is the most common liquid, and we will quote this value for 0, 20 and 40 degree centigrade. For 0 degree centigrade, it is 1.78, for 20 degree it is 1.0, and for 40 degree it is 0.651. So, if you see that the viscosity goes down with the rise in temperature for water, and these are the temperature mentioned corresponding to the fluid, and these are the values of viscosity that are noted. As you see that glycerin is of course very dense and so is very viscous. So, now in this connection let us do one law called as the Poiseuille's law. So, this quantifies viscosity or rather the flow of rate of flow of a liquid through a pipe or a tube and the quantities that it depends upon, and links it to the coefficient of viscosity. Okay. So, let us consider a pipe which could be, you have seen those hypodermic syringes which are pushed into the veins in order to give an injection by which a medicine is administered. And let us say this is some kind of that kind of a pipe which has a length L. Here we do not talk about the area of cross section, but it is same to talk about the radius, and the pressure is measured here by say some gauge is P2, and the pressure measured here again by some gauge is P1, where P2 is greater than P1. So, now we want to know the rate of the flow of the fluid through this pipe and how it depends upon these quantities such as P, R and L. So, this flow rate, it is usually mentioned denoted by Q, the flow rate of the fluid through the pipe of radius R length L and having a pressure difference of P2 minus P1 along the length. So, this flow rate Q, so Q is proportional to P2 minus P1, that is, the more pressure difference is, the flow rate will be higher. It is also as we have seen earlier, it is proportional to the 1 over L, the length of the tube, and little surprisingly it is proportional to the 4th power of the radius of the tube. So, this is the radius of the tube. So, it is proportional to the 4th power, and the flow rate is written as so, the proportionality constant has got a slightly non-trivial expression. So, it is like pi r 4 P 2 minus P 1 divided by 8 eta L. Okay. So, this is my constant of proportionality, which is not simply one can write it with some eta prime, but that eta prime equal to pi by 8 eta. So, this is the constant of proportionality, and it depends on the pressure difference between the two ends. So, we have said that this pressure is P 2 and this pressure is P 1. It is inversely proportional to the length of the tube. It is directly proportional to the 4th power of the radius, and this expression is called as Poiseuille's law. So, let us do a problem on surface tension. To remind you, surface tension is the force per unit length, and it basically works along any line on the surface of a liquid, and we have seen a number of consequences of having surface tension. That is, even a small water filled balloon can actually float on the surface of the water, or an insect can actually walk on the water without getting drowned, and all of them may have more they could be more dense than the liquid or on which they are they are being supported at the surface. And so, let us do a problem on surface tension. So, the surface tension, this is an example problem. The surface tension of a soap solution is 0.03 Newton per meter. What amount of work is required for producing a soap bubble of radius 0.05 meter. So, there is a soap solution and we need to make a bubble out of it of this radius 0.05 meter. There is certain amount of surface tension and the surface tension is given by 0.03 Newton per meter, and we need to find out the work done in order to do that. So, the solution can be written as follows. So, the work done in making a bubble this is equal to the surface tension this we have discussed earlier, that the surface tension is also defined as work per unit area or joule per meter square. It has a unit of joule per meter square. So, there is surface tension into the total surface area. Now, this total surface area is important because there is an inner surface and there is an outer surface, but the bubbles are very thin. So, we can take the radii of each of the surfaces to be same as this radius. However, the total surface area will be twice the surface area of the sphere that is having this radius. So, this, as I told, that this means that the surface tension into inner plus outer surface area so this is equal to 0.03 Newton per meter into twice and a 4 pi twice because inner plus outer, and this will be 4 pi r square, which is equal to 0.05 meters square. And when you work this out, this becomes equal to 1.884 into 10 to the power minus 3 joules. So, that is the work done or that is the work required to produce a soap bubble of a 0.05 meter radius, where the surface tension of the liquid or the solution is 0.03 Newton per meter. So, let us recapitulate that what we have learned about the properties of fluids in this chapter. And we have started our discussion with the definition and the importance of density and specific gravity. And we have seen what the definitions are and what are the for some common fluids, what are the densities and the corresponding specific gravities. Then we have very elaborately talked about pressure. So, we have talked about pressure exerted by a fluid at a distance or at depth h from the surface, which is given by P equal to h rho g. Further, we have also talked about, or rather demonstrated how the pressure due to the atmospheric atmosphere changes with the height as we go away from the sea level. So, having discussed pressure, we have then talked about measurement of pressure and what are known as gauge pressure, etc. So, we have talked about of course, atmospheric pressure and gauge pressure, and we know that the pressure that is measured is has to be the atmospheric pressure has to be actually added to that to the gauge pressure in order to calculate the exact pressure. So, if at some place the pressure is quoted as say 2.7 atmospheric pressure, the actual pressure is 3.7 atmospheric pressure, because 1 atmospheric pressure has to be added. Then we have learned the interconnection or rather the different units of pressure or rather different representations of pressure, and the pressure can be expressed in bars, or pressure can be expressed in Pascal, or pressure can be expressed in kilopascal, or it can be expressed in atmospheric pressure, or it can be expressed in so many millimeters of mercury, and what are their relations, interrelations between one unit to another unit. We have seen that. Then we have talked about some commonly used pressure devices, such as so measurement of pressure, and so we have talked about barometer, we have talked about a U-tube manometer for measuring pressure, and then we have talked about Pascal's principle. So, which tells you that the pressure applied to a confined fluid actually increases the pressure throughout the volume of the fluid by the same amount, and this has very important applications in the automobile industry, where it is used, the hydraulic brakes are used to stop a speeding car, or there are hydraulic machines which are required to lift heavy objects such as trucks or other heavy vehicles, where a small pressure can be applied at one end of the U-tube, which is thinner, and the pressure gets transmitted, and at the other end of the U-tube, which is much broader, one gets a lot of force by which one can lift a heavy vehicle, even a very heavy vehicle. So, these are some of the applications of Pascal's principle, and then we have also talked about equation of continuity. Which says that for an incompressible fluid, non-viscous incompressible fluid, the product of the area of cross section through which the fluid is flowing multiplied by the velocity of the fluid will remain constant. And then we have talked about buoyancy and Archimedes principle. Which nicely shows that the weight of the, or rather the reduction in weight of an object inside a liquid is equal to the mass of the, or rather the weight of the displaced liquid. And we have proved that using some general consideration. After that, we have talked about surface tension. And surface energy. Here we have defined surface tension and surface energy and said that actually not only inside the fluid, it is also the surface of the fluid acts quite interestingly, and it acts like a membrane which is stretched and under tension. So, it happens because of the surface tension that acts at the surface along a line and is defined as the force per unit length. And we have seen some very interesting consequences where liquids such as water and mercury can be distinguished by the angle of contact that it makes when it is kept in a beaker. So, what happens is that water level rises a little towards the end, which is because the force of adhesion is more for the water molecules. So, the water molecules bind tightly with the molecules that the beaker is made of, whereas for the mercury it dips a little bit towards the end, and that tells you the force of cohesion among the molecules of the mercury is more than the force of adhesion. And these are, so this way one can talk about, or one can distinguish between various liquids, and we have defined an angle of contact in that context. So, this is called as capillarity. And then we have talked about Bernoulli's equation. So, Bernoulli's equation has been derived, which says that the kinetic head plus the potential head plus the pressure head should remain constant for a non-viscous fluid, for a streamline flow, and this has important consequences or rather applications, as one of the applications was seen in venturimeter. Venturimeter shows or rather measures the speed or the velocity of a fluid through certain region of a pipe that it's flowing through. And we have also seen it in the context of blood flow to the heart, and why there could be chances of heart attack when because of the increased blood pressure through the arteries, especially the arteries that carry blood to the heart, which are known as coronary arteries. And finally, we have looked at the viscosity, where we have defined viscosity, which is a property of the fluid, because of which different layers of the fluid moves with different velocities. And if you are talking about a flow through the pipe, the central lamina moves with a greater speed, with the speed going to 0 for the layer that is in contact with the inner periphery of the pipe. And in that connection, we have defined coefficient of viscosity and also defined Poiseuille's formula, which talks about the flow rate and how it depends on the pressure difference between the two ends, on the length of the tube through which the fluid is flowing, or on the radius of cross section through which the fluid is flowing.